discuss the time domain analysis of systems. So we will look at how to represent systems in a more formal way, and we will discuss later on how to calculate the response of a system to a particular input. This part is scattered a little bit between chapter 1 and chapter 2. There are like last few parts of chapter 1. They address part of this material, but mostly it's in chapter 2. So I combine them into one presentation. So this presentation spans a little bit of chapter 1. So there are two ways to describe a system. There is and we discussed briefly about this at the start of the course in the introductory part. So there is an external description of the system, so you only care about how to calculate the output from the input, or how do you relate the output of the system to the input, or how to figure out what's going to be the output for any particular input. This is called an external description or input-output description of the system, right? There are two ways to calculate this kind of description or this kind of representation. Either you go through these three steps, or you do it by just measuring the inputs and the outputs for particular defined inputs or particular types of inputs that allows you to generalize later on for any type of input and calculate the output accordingly. يا شباب اللي يخش متأخر لو سمحتوا يقعد من سكاته. خلاص مفيش داعي للدوشة دي. Okay. So what's the first one, which goes through three steps? Basically, you try to relate all the signals across the system internals itself to each other, knowing the different components and how they respond to different. عليكم السلام ورحمة الله.
كانش موجود يا دكتور. كانش موجود.
كانش موجود. Okay. So one way, the one that goes through these three steps is, you know the internals of the system, you try to represent the relation between the signals and the different components of the system itself, and then you eliminate the parts that you don't need through some set of equations or whatever, until you end up with a relation between the input and the output. Simplest example that you do this, or you apply this to every day, is when, for example, you have, let's look at this circuit, right? So you have some source here, x of t, and then you have maybe capacitor, resistor, right? And continue the circuit, and then you are interested, for example, your output is this. So this is your y of t. The output from the system is the voltage across the resistor, right? And the input to the system, or to this system, is some applied voltage at the source, right? And what you need is the relation between the input and the output. So you start analyzing at every single component. So you know, for example, that across the capacitor, if you have a certain voltage C, the relation between this voltage and the current is what? What's the relation between the voltage and the current on a capacitor? Yeah, so I that goes through the capacitor, which is the current going through this circuit. What's the relation? IC is equal to dV by dt, right? dVc by dt. So the current going through the capacitor is equal to the capacitance multiplied by the derivative of the voltage, right? Okay, and then this allows you to know the current. Now you know that this same current is going through the resistor R. So if this capacitor has a capacitance C and this has a resistance R, then you know that the voltage across, which is the output voltage that you are looking for, is equal to this IC multiplied by the resistance. So this says that, okay, V output is equal to C dVc by dt, right? This is the output, and then multiplied by the resistance R. So now you were able to create some relation between the output and the voltage across the capacitor. Now you have another relation that relates those quantities to the input. Yes? Okay, so the sum of the voltages across, that's another step that you have to do, right? So one step was figuring out what happens at every element. The other step is like Kirchhoff's law, for example, right? The sum of the voltages across the whole loop, or the sum of the currents. So you apply one of those according to your situation, if you are dealing with a node or. So there are two things that helps you achieve this analysis, right? Number one, the relation between the signals at every single component, and then some constraint or some collective relation when you interconnect components together, right? If you look at the slide, these are the first two steps that are mentioned in the slide over here. So study the relationship between different system variables on each component, determine various constraints on variables when components are interconnected together. You end up with a set of equations. So let's continue what we were doing. The coming one says that x of t plus vc plus v out, which is y of t, your output, right? All of this should be equal to, the sum across a loop is equal to 0, right? That's your voltage loop, right? And then accordingly, you can figure out a relation between y of t and x of t. How would you do that? So you want to get rid of this because it's an intermediate, right? So if you want to get rid of this, what would you do? There is a relation here between y of t and vc, right? If you want to convert this relation to get rid of vc, what would you do? It's the integral, right? Okay, so you end up with some relation here that says x of t, right, plus 1 over rc multiplied by the integral of y of t dt, right, plus y of t. Okay. All of this is equal to 0. Now you have a relation between y of t and x of t. So you can, from this, it's a complicated relation, but this is a relation that shows you how to relate the input and the output together. So we only have inputs and outputs only in this equation, right? The output y of t and the input x of t. And if you want to get this relation without the integral, just take the derivative of everything. You end up with the derivative of x, right? Minus 1 over r, sorry, 1 minus?
You said plus, but you're
Plus,
minus.
sorry. Okay, plus 1 over rc, the integral here, when you take the derivative of this, it becomes 1 over rc y of t, and when you take the derivative, it becomes a differential equation that relates the inputs to the outputs, right? Okay. Accordingly, you have established an input-output relation by applying these steps. That's one way to do it. The other way to do it is, for this system, you know that a particular input, that's what we are going to study in a few lectures. You know that there is a particular input which characterizes the system, which allows you to figure out everything about this system, including being able to calculate the output. So you apply that particular input to the system, and then you measure the corresponding output, and that allows you to get directly a relation between the input and the output that can be generalized, not only for those specific inputs and outputs, it can be generalized to any general input and output, and accordingly you get an input-output relation without really studying the elements inside the system, okay? So that's the other way, which is measuring inputs and outputs for specific characterizing inputs, and then accordingly you get the relation. Final idea is, if you have an nth order system, meaning that it's a system of second order, third order, so which means how many derivatives you do, right? If you have an nth order system, it's going to be described by an nth order input-output relation. It's one relation that relates the input to the output. If it's a first order system, it's going to be a relation with first order. If it's a system with capacitor and inductor, for example, that's a second order system. You will have a second order equation. If it has capacitor, inductors, and some other elements that adds to the representation, you will end up with an input-output relation of the third order, and so on. Yes?
What do you mean by nth order system or equation?
It's a bit difficult to describe. Maybe when we talk about the states of the system, it would be clearer. But it means that it has n components that are affecting the performance of the system. It this case, we consider the resistor as a very passive component, so it doesn't really affect anything, right? But capacitors, inductors, maybe later on if you have amplifiers, or if you have transistors and so on, these kind of components are affecting the order of your. Remember when you studied, did you study filters in your electronics,
Yes.
right? So filters, if you have RC and then another RC and then another RC, that's a third order filter, right? If you have more of those, then you have higher order filters and so on. So it depends on the number of critical components or components that really affects the input-output performance of the system, other than simply scaling them. It differentiates, it integrates, and so on. Not just multiplying the value by a constant. That's not changing the value. Okay? Resistor always multiplies the value, so you convert from current to voltage on resistors by simply multiplying by constant, right? But for capacitors and inductors, you add differentiation or integration. So it is a different representation. So that more or less represents what we mean by the order of the system. Okay? So for this input-output relation, depending on the order of your system, the number of critical components, the number of time-affecting components is represented by the order of that equation. Okay? Any questions about this input-output relation representation? Yes?
حضرتك قلت نقدر set of inputs ناخد الاوتبوتس ونعمل generalization.
Yeah.
هل لازم السيستم behave the same for all inputs؟
It is going to behave the same for all inputs if we consider particular types of systems. And we are going to consider particular time, linear and time invariant systems only. Okay? So this is, again, the same example that I mentioned, but it's described here in details until you end up with the differential equation that represents the system at the end. This one has, I think this derivation does not comply with the figure, because this derivation is an RLC, and the figure is wrong. So I will correct the figure, Shabab. This figure is wrong. The other figure has an L as well before you go to the C. So this figure is wrong, I'm going to correct it. So for an RLC circuit, like the one that you see here, if you want to relate the input to the output and you do the calculations, this is the derivation that you will go through, and you will reach something similar to what we did in the previous simple example that included only one capacitor, right? Notice here that because you have two time-affecting elements, the inductance and the capacitance, you end up with a second-order system. So it has the second derivative included in the equation. For the previous system, because we had only one critical element, which was the capacitor, so you ended up with an equation that has only the first derivative on. Okay? Okay. The other way to represent system is to look actually at the internals of the system itself and try to do a representation that describes what's happening inside the system. Okay? And typically in that case, the system is divided into components. We call each one of them a subsystem, right? And then for each one of those subsystems, they are interconnected together, and you are trying as much as possible to describe the internal behavior with two important objectives: that you can affect every single component inside with the input, and we call that the controllability of the system. And when you are reading the output, any change on those internal components should reflect on some change at the output, and we call that the observability of the system. So when you are describing a system internally, two things, right? Number one, you are trying to give a description that talks about how the signal behaves at every single component. It's not simply just input-output relation, okay? And number two, you are trying to achieve in that representation as much as possible that the input affects every single component of the system, and that the output that you read is affected by any component in the system. Accordingly, you can actually figure out the behavior and the internals of the system just using input and output measurements, right? If you manage to make sure that the input is affecting every single component and the output is affected by every single component, then by changing input and output, you can actually figure out the dynamics of the system, okay? That's called the internal description, and the most common or the mostly used in engineering representation is called the state space representation. I don't know if you heard about this maybe in your math course, if you took the mathematics for engineering course. State space representation describes a system, and it is an internal description. It uses something called the state variables. These are critical signals inside the system that if you know them, it's sufficient for you to know every other signal inside and outside the system. So the states of the system are basically some variables that represent some important signals inside the system itself across the different components, right? And those signals or those variables are sufficient. If you know them, you can calculate everything else from those variables. You can calculate every other signal across all the components, and you can calculate the output. Okay? Of course, taking into account the input going into the system. Yes?
حضرتك تقصد إذا عرفت بعض الانبوتس بقدر أعرف البيهيفير بشكل عام يعني؟
Mission behavior. Some of the signals inside, I have a system, I have an input, and then different subsystems inside, different points and interconnections between subsystems. I don't need to know all the variables inside. It's sufficient for me to know certain critical variables. If I know those, I can calculate everything from those. We'll take an example to show what I mean by this, okay? So this is what's called the state space representation. Typically, this state space representation has two sets of equations, okay? One set that relates those critical variables to each other. We call these the state equations. And then other equation or equations that relates the outputs to the states, okay? So now, if I know the states or the state variables, of course, and I need to know the input, I can immediately calculate the output of that system, right? If I have multiple outputs, I can put an equation for each one of those. This is called the output equations, okay? So we have two sets of equations for any state space representation of a system. The first set of equation relates the state variables together. Let's say that the state variables in a particular circuit were found to be the sufficient variables that you need to know, were found to be the voltage on a particular capacitor and the current going through a particular inductor, right? Now, using those two are going to be related to each other and to the input using a set of equations. These are called the state equations. So how to figure out those two variables from the input and how they relate to each other. This set of equations is called the state equation. Now I'm interested in that particular circuit to measure the output across a resistor somewhere or across that capacitor or across some combination of elements or whatever. This output is going to be represented as a function of the state equations and the input, and accordingly, once I know the states, I can figure out the output. Okay? That's called the output equations. The solution of the system starts by solving the state equation. Typically, the state equations are differential equations, right? You solve those, then you figure out the representation of each one of those state variables as a function of time. Then if you know them and you know the output equations, you simply substitute that solution into the output equation to calculate whatever output you are interested in. Okay? Again, in case you are representing an nth order system, now the description is slightly different. Rather than having an nth order equation, in state space representation you end up with all the equations first order, but the number of equations grows as the order of the system grows. So in the state space representation, we have, for an nth order system, we have n simultaneous equations, so multiple equations, but each one of them is first order. The simplest way to understand why this is the case, when we do state space representation, if I have something like this, like what we had in the previous slide, for example, y double dot of t plus, let's say, 3 y dot of t plus y of t equals, let's say, x dot of t, for example, and this is a state equation, I can simply break this, which is a second order equation, I can simply break this into two equations, right? I will just call y double dot, I will call this as maybe something called z of t. And you know that y double dot is the derivative of y dot, right? So you know that z of t is equal to y dot dot, right? So it's the derivative of y dot. And accordingly, I will replace y dot, with z of t. Y dot, I will replace it with z of t. And then I know that y double dot of t is equal to y dot derived one more time, which is equal to the derivative of z of t, right? So now I can write this equation that you see up there, I can write it as two equations. What are those two equations? And each one of them is a first order equation. I will go to this one, and then y double dot is actually z dot, right, of t, plus y dot is z of t, right, plus y of t equals x dot of t. This is a first order equation. And the second equation that I just created was this guy, that z of t is equal to y dot of t. That's another second order equation. First order equation. So I ended up with two first order equation in two states, right? Now I have state z and I have state y, right? So I have two state variables, but for each one of them, they only appear as a first order derivative. So now I mapped the second order full representation into first order but multiple equations, just to tell you mathematically why this is the case and why they are equivalent. Okay? But there is a difference between state space representation and input-output representation in the fact that in state space representation, you know everything about the internals of the system. While in input-output, you only relate the input and the output, and you don't really care what are the internals. The internals can be anything. Okay? Yes?
The state space order equations are always first order.
First order.
But the output can be any order.
Yes. And the order in input-output depends on the actual order of the system, if you did the derivation correctly. And in the state space, the number of equations, the number of state equations, not input-output equations, the state equations. You have two sets of equations, right? The state equations and the output equations. Output equations depends on the number of outputs. That's a different story. But the state equations, the number of those equations, each one of them is the first order, and the total number is equal to the order of the system. Okay, here is an example, so you know what I mean by state variables and what is meant by state equations and what's meant by the output equations and so on. Okay, so for this RLC circuit, okay, you can, there is a way to do this, but we're not going to deal with this in this course. If you study a control course or maybe some other courses that focuses more on the state space representation, you will be looking at that. But you can figure out that if you know the voltage across the capacitor, call that Q1, and the current going into the inductor up there, call that Q2, then you can calculate every other current and voltage across this circuit. Okay? So you only need two states for this circuit. Another way to look at this circuit includes two time variable elements, right? The inductor and the capacitor. Typically, the state variables are related to those elements, and this is a second order system, so you know that you need two equations, two state equations, which means that you need two state variables. Otherwise, if the number of equations is greater than the number of variables, or the number of equations is less than the number of variables, the solution of the system becomes either there are many solutions and there is no unique solution, or it becomes probably impossible to solve if you have more equations than the number of variables. Yes?
We take only capacitor and resistor and load as variables.
We take only what, sorry?
Capacitor and the load as variables. We don't take resistors.
Yeah. Resistors are simple elements that does not, I described this earlier, right? Resistors are elements that causes only a multiplication by a constant. So they do not affect the order of the system. Capacitors and inductors does differentiation and integration, so they affect the order of the system. Yes?
نعتمد على بالعدد ولا بالنوع؟
لا العدد. يعني if you have two capacitors it means
2 time
two, yes. Okay? So it's not only, that's why when you have RC, 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 this is a third order, right? It's not a single order, yes.
عندي 2 parallel capacitors ما اقدرش ادمجهم في واحد خلاص.
تقدر تدمجهم بس once you combine them you lost the representation of internal. The idea of combining things, you do this when you are interested to relate only input to output. But if I want to know what's happening at the internals of the system, I don't do that.
يعني مش لو عملت كده مش هقدر.
You will get some representation, but it's not sufficient to represent every single component or every single signal inside the system. Okay? خلاص. Any other questions يا شباب? You might end up sometimes in similar situations like this with the system unobservable, which means that even though you keep them separate, but because of the relation between them, you cannot really differentiate the effect on one as opposed to the effect on the other. And that we call that, which means that the output is not going to be affected by a variation on this or that. It's the same. It's going to give you the same effect, right? So in that case, we call this system unobservable system because you cannot represent every single variation inside it to some effect to the output. خلاص؟ يعني I just want to give you a general description about the state space representation, but as long as you understand the general concept, we don't need to delve that much into that part, even though you need to know that it's there and it's important, because our focus on the course is going to be on input-output relation. So in a couple of lectures, we will forget everything about state space representation, differential equations, everything. We'll go back to input-output relation, and we solve that using just linear regular equations. No more differentiation or anything. Yes?
Should we know how to convert from output to state equation?
Convert? No. No. Okay.
So there's no relation between.
There is, but that's not what we need to do here. Okay? So here you will be told that if you have this system and the states are this variable and that variable. So now once you know the states, your function is going to be figure out the state equations, so the relation between the different states. And if you are interested in that particular output, what's the output equation as a function of the states? Okay? So even here, we have like equations that represents every single possible output as a function of the states. Typically, you are interested only in one output, maybe V3, maybe VL, that's your output. You don't care about the others, right? So these equations, you don't need all of them. If you have a particular defined output, you just need to represent that output as a function of the states. Okay? Here it's just for demonstration and analysis, but not really what you are going to be doing in a particular system. Anyways, so these, if you look at this, right, these relations are X is the input, right? So V1, the voltage across the resistor is equal to the input voltage minus the voltage across the capacitor, Q1, right? And the current going through that is, again, this same voltage, V1, divided by the value of the resistor, right? So it's also easy. V2, if you want to calculate the value of V2, which is the voltage across that resistor, the 2 ohm resistor, it is actually equal to the voltage across the capacitor. So it's directly equal to Q1, right? You want me to point here? It's just simple circuit analysis, right? So the voltage here is simply the voltage here, that's Q1. So that's this equation. I2, the current going through this resistor, right, is equal to the voltage across the resistor divided by the resistance value, and we agreed that this voltage is Q1, so it's equal to Q1 divided by 2, right? The current going through the capacitor, IC, is equal to the difference between two currents. What are these two currents? Sorry, three currents, sorry. It's a combination of three currents, or basically Kirchhoff's law. So you have I1 going here, right? You have this IC going here, and you have I2 going here, right? Okay. So this IC is equal to the I1 going in minus I2 is going here, right? While Q2 is the one going here. So the sum of those two is going to be the current going through this branch, right? So the current going through this line is the sum of I2 and Q2. We agreed that Q2 is the current through the inductor, right? So if you add those two, it gives you the current here. When you subtract that, it becomes minus I2 minus Q2. So we are trying to say I1, right, minus I going here, which is the sum of those two. So minus I2 minus Q2. Okay? This will give you the current going through the capacitor. I3, the current going into this resistor, right, is equal to the same current going here, right? So it's Q2. Because we agreed that the current going through the inductor is Q2. So basically that's the same current going through the resistor. And then the voltage across the resistor is the resistance times the current. So 5Q2. And then finally, the last thing that we need to figure out is the voltage across the inductor. And that voltage across the inductor is equal to the difference between those two voltages, right? Q1, which is the voltage here at this point, and it's the same as the voltage here, that's Q1, right? Subtracted from it the voltage across this resistor, which is 5Q2, right? So these two voltages, the difference between them gives you the voltage across the inductor, okay? Now these are, this allows you to calculate any voltage and any current everywhere as a function of the states, right? Typically, you don't need all of this. What you need is going to be, if I'm interested in this, let's say V3, then I need only this equation. And I don't need all the others at that stage, okay? Now the other important thing is how to relate the states to each other, right? And that is going, in that case, you are going to use the relation between, notice that here, we were trying to use voltages and currents without any incorporation of differentiation or integration. So without incorporating the actual behavior of the inductor and the capacitor in terms of relating voltages and currents. When we are trying to do the state equations, we are trying to get a relation between Q1 and Q2 and the input only. So these equations should include only Q1, Q2, the two states, and the input. That's it. They should not include any other variable. And if you try to do so by incorporating the relation between the current and the voltage across the capacitor and the current and the voltage across the resistor, you should be able to end up with those two equations. In the book, there are more details, but for the slide here, it takes a long space to actually include the details of deriving these, but it's very simple. Just incorporate the extra differential equations that relates the current and the voltage, and the integral equation of the differential equation that relates the current and the voltage in the inductor, and then you should be able to come up with these two equations. And those are the state equations that relates the states and the input, okay? Why it was sufficient to actually pick only two states, and why particularly Q1 and Q2 are the suitable states to represent this system, kind of out of the scope of this course, but intuitively, here we have two elements that have time effect, the inductor and the capacitor, and typically the main independent variable for the capacitor is the voltage, and from that we can deduce the current, and for the inductor, it's the opposite. If you want to write it as a derivative or differential equation, then we take the current, and from that we derive the voltage, right? So that's why only the two variables about the inductor and the capacitor, because they are the two time elements into that circuit, and why we pick the voltage for one and we pick the current for the other, because of the way they are related to each other. We want always the relation to be a differential equation rather than an integral equation. Even though an integral equation, you can always convert it at the end to a differential equation, okay? So this is kind of intuition. In reality, how do you do that and how you reduce the system and how you figure out, there is a systematic way to do it, but it's outside the scope of this course, okay? Yes? We only need this equation that relates the output, which is V3, to the states. We only need an equation that represents the output that you are interested in terms of the states of the system. This is different from this. This is called state equations. You need those, regardless. You pick two states, you need two equations that relates those two states and the input to each other. Okay? So you need two equations here, the state equations. For the outputs, you don't need all of this. You just need which output you are interested in this one. Then you need to see how this can be calculated from the states and the input. And simply this does the function for you. It says if you know Q2, you will immediately know what's the output, right? You don't need any more information.
يعني عشان Q2 دوت ديت هستعمل بس هشوف V3 equals to 5Q2 واستعملها بس.
مش فاهم.
يعني second equation اللي هي الاوتبوت equation.
ايوه. This one.
مش هستعمل
تحت دي مش output equation. دول state equations. This is state equation. This is state equation. دول are called state equations, not output equations. They relate the states to each other and to the input. بس. They don't look at anything related to the output. The output equations are relating every possible output to the states and the input. تمام? If you are interested only in one output, then all these equations, you don't need them. You only need this guy. Because you are interested in this one output. If I'm interested in this one output, اللي هو VL, then I need only this equation. And I don't need all the others. So it depends which output you are interested in. خلاص? Okay. Any other questions? Yes.
This equation جبناها منين؟
Which one?
الأوتبوت
Output? أنا مشيت عليهم واحدة واحدة.
احنا فاهم بس
I did them one by one. The ones that I didn't do in details are the state equations. And you can look up the details. Just simply put two extra equations to those output equations and try to do elimination and substitution until you get only two equations in states and input. That's it. You don't need any other variable to be in the equation. You will end up with those two. طيب. Again, when we represent a system using state space representation, the description or the classification as observable or unobservable, controllable or uncontrollable. Remember, a controllable system means that through the input, you should be able to affect all the system components, right? Or all the signals of the system. If there is a particular signal flowing inside the system which is completely not affected by the input, then this system is called uncontrollable, because there is part of its behavior that you cannot affect by the input. Okay? Now, when we do the state space representation, we forget about the elements and the components, and we look only at the states. Okay? If the input is affecting every single state, or in other words, if when you look at the state equations, you see that all the states are dependent on the input somehow, either directly or indirectly, then in this case, this system is controllable. So for a controllable system, the states look at the state equation. If you see that all the states depends on the input, then this is a controllable system. Okay? If this is violated, so if the states, some of them are independent from the input, then this is an uncontrollable system. Okay? The other way, when you want to check the observability, you look at the output equations. And if you see that the output depends on all the states, then this is an observable system, because any change in one state is going to cause a change in the output, right? If the output is independent from some of the states and affected only by the others, or independent from all the states, then in this case, this is an unobservable system, because the changes in the states might not reflect, some changes on the states might not reflect on the output. Okay, so you cannot observe if the state changes by simply observing the output. That's why we call it unobservable. الكلام ده مهم امتى؟ الكلام ده is very important when you are trying to study something like control, right? You know that there are critical parameters of your system. You want to make sure that these critical parameters, if something happens to them, you can see that in the output. Otherwise, you will not be able to diagnose that something wrong went into the system. And then, if you know that these parameters are critical, you also need some access to them so that you can adjust them. This is called the controllability of the system. How would you do that? Through the input. So your input to the system can adjust those parameters to make sure that the system performs as desired, right? Yes.
دكتور لو في شيء تغير بالسيستم ما شفته بالاوتبوت ايش بدي فيه شيء ما راح ياثر طالما تغير ما اثر بالاوتبوت ما منه فائده
لا هيأثر. هو الاوتبوت حاجه يعني الاوتبوت that you are measuring is something with desired product من السيستم ده حاجه ثانيه. So we are not really talking about what's your desired product. We are just talking about output signal, measured signal. تمام؟ But it might be that the product that's coming كلامك صح. If that change is not going to affect the product or the intention from that system, that's a different story. تمام؟ Yes. So هنتكلم هنا على input or output signals, not really the product coming out of the system. Okay. Any other questions يا شباب؟ So if you go to the example of the previous slide, right, you will notice that we had okay. That's my mistake. I should have written the equations here again. But anyways, the reason I'm stumbling is that this causes. So to summarize what I just mentioned when we went to the previous slide, you will notice that in the state equations, the first equation shows a relation between Q1 and the input. The second shows a relation between Q2 and Q1. But since Q1 is already a function of the input, this means that when you change the input, Q1 changes. And since Q2 is a function of Q1, it's also going to change, which means that this system is fully controllable, right? Both states are affected by any changes in the input. When you look at the output, assuming, for example, we are interested in output V3, the voltage across the resistor, as we looked at in the previous slide, you will notice that the output equation is just a function of state Q2. But again, because Q2 is a function of Q1, so Q2 is definitely, right? So the output is definitely also a function of Q1. Because once Q1 changes, it's going to cause a change in Q2, which is going to cause a change in the output. So this system is also fully observable because the output is affected by any change in any one of the states. Either Q2 only changes, or Q1 changes, is going to cause a change in Q2, which is going to cause also a change in the output. Okay? Now again, for a more formal study on state space representation, the representation is going to go through some matrix representation, and you have 4 matrices representing the system. 2 of them are related to the state equations, and 2 other matrices are related to the output equations. And then using the properties of those matrices, you can simply mathematically show whether this system is observable or whether this system is controllable and so on, right? But here we are doing it just roughly to get you to know the concept, but we are not really going deep into the classical approach to state space representation. That's a full course study by itself. Okay, so we are not going through that big mathematical representation, just to get you to know the concept in a very simple, intuitive way. Okay. Now, typically in this course, we are going to deal with linear and time invariant systems. Remember when we discussed the properties of the different systems in the last lecture? We said there is one property called linearity, and there is another property that we cared about called time invariance, right? And in general, any system which is represented by first order differential equation, right? And that system is, sorry, not first order, linear differential equation. So this means that none of the components of that, not first order, sorry, linear differential equation, which means that the different components are not raised to power 2 or 3 or whatever. So you don't have the first derivative or the second derivative squared, or you have the input squared or the output squared. It's a linear differential equation, and the parameters of that differential equation, those parameters are constants. They are not a function of time. This system for sure is going to be linear because the relation between the input and the output is linear, and since it's represented by linear differential equation. And this system is going to be time invariant because the different system parameters, the C's and the constants, the A1, A2, and the B, and so on, all of these are not function of time, which means that if you shift the input, the output of this system is going to shift with the same value without any other change. That means it is going to be time invariant. So any system represented by linear differential equations such that the parameters of that differential equation are constants, they are not function of time, we know that this system is linear and time invariant. Okay? And most of the physical systems that we deal with can be sufficiently represented by linear differential equations. Okay? This includes most of the circuit representations. This includes most of the mechanical systems that has springs and stuff like that. We always have a some order differential equation that represents the behavior of those systems. This includes something like hydraulic systems that we use to, for example, lift things or to move things or to braking systems and so on. So all the hydraulics are also represented by linear differential equations. They are not necessarily first order, they can be of any order, depending on the order of the system, but they are linear, constant differential equations. The parameters are constants here, okay? So we will focus on this type of system. Now, again, from your math course, you know that solving these equations is quite simple. You can just assume that this derivative, right, is an operator, right? And then you represent the d by dt by an operator called capital D. And then if you have a second derivative, it becomes d squared. If you have a third derivative, it becomes d to the power 3. Up to the nth derivative, we call that d to the power n, right? So here we are representing what you see up there in the original representation of the system with a polynomial, that's the target. So we are representing this equation with a polynomial-like equation where we have the derivative parameters represented as a polynomial and then multiplied by y of t equal to the derivatives multiplied by the input, right? Okay. And we can simplify this by saying that this is a polynomial q of d here for the output, and there's another polynomial applied to the input p of d. Okay. These polynomials are of the order that corresponds to the highest derivative on both sides. So for the q of d, it's of order n, and for the p of d, it's of order m. Okay? Generally speaking, you see that in the next slide, for those systems, we always want the n to be greater than or equal to the m for practical reasons. Can anyone figure out why? It's not an easy question, by the way. So why in practical systems we want the derivatives with respect to the input, this polynomial, the output, we want this polynomial to be equal or higher order than this polynomial. So typically n is greater than or equal to m. Why? Yes?
To be able to make more equations.
No, not very.
Stability?
Stability. Why it's related to stability? صح. Initial answer correct. Why? How do you relate this to stability?
الحظر.
طيب. Let's discuss two cases. Building on your answer. تمام? If I have more derivations, so for example, the output reaches a third order derivative, okay? While the input reaches a second order derivative. This means that generally speaking, the output is calculated, generally speaking, by deriving the input or by integrating the input. Integrating the input, right? The opposite. If here we reach a higher order, then generally speaking, the output is derived by taking the derivative or differentiating the input, right? Why a differentiator system is worse than an integrator system, particularly in relation to stability.
Because the shift plus C, when you take the derivative, you will have the plus C. You will not get exact.
Where is the problem in derivatives?
Change the time value, it's still very.
Yes. So the problem with derivatives is when you deal with things that has abrupt change, like a unit step, so something starts at any point, or when you deal with high frequency components, because the derivative of high frequency components gives you what? حاجة عندها very high frequency. What's going to be the derivative? Higher or lower? Whenever you have higher frequency change, like the abrupt change, for example, you have more value of the derivative, which means that in general, even though your input might be bounded, but because it has some abrupt change, even though it's still bounded, or it changes very quickly, the output might blow out, right? Why? Because the output is not dependent on the input, it's dependent on the derivative of the input. And in case of quick change, This means that even though the input value is not big, but it changes quickly, you take the derivative, you get an output value which is blowing to a very high value. So if it's an amplifier, it's going to saturate. If it is a motor, a DC motor specifically, it might actually break down just because of higher torque, and it just speeds up without any slowing down until it gets apart from each other, and so on, right? So these, in general, we are interested in systems that have either same order, or the output order is higher than the input order, differentiation order, because these are integrator systems. These are more stable to quick changes. Okay? While systems that are dealing with differentiators or have a differentiation behavior, they are quite unstable, especially for quick changes, abrupt changes. Okay?
So
Yes.
حاجات لما تكون الديريفاتيف عليها تربيع او باور ما بتكون linear time.
مش كده. مش ده. مش النوع ده. ده الاوردر اوف ذا derivative. What I'm talking about is you have this derivative and it is squared, for example. So the equation is no longer being linear. تمام؟ Okay, here I'm just mentioning those things that we mentioned about the orders of the system. So for practical systems, m is less than or equal to n. M is the order of the derivative of the input, and n is the order of the derivatives of the output. Okay. Now this system, since we agree that this is a linear, we said that this system is linear and time invariant, right? Remember earlier we have discussed that any linear system has this nice property which is called the decomposition property. Do you remember that? What's the decomposition property? It says that if you want to calculate the output, the total response from this system, right? Then you can divide that into two separate steps and you simply add them together, right? You can calculate the output from the system without any input. So you assume the input goes to 0. And you only calculate output that comes out of the system due to initial conditions, right? We call that the zero input response. And then you set the initial conditions to 0, right? And you calculate the output from any particular input, and we call that the zero state response. The total response of the system with certain inputs and certain initial conditions other than 0 is simply the addition of those two responses together. If the system was not linear, you could calculate this by itself. You could calculate this by itself, but there is no way that tells you how to combine them to get the total response. If the system is not linear. If the system is linear, after we calculate this and we calculate this, we know that we simply need to add them together to get. So the effect of the linearity is the fact that we can combine those just using a simple addition to get the total response, right? Now, if the system was non-linear, yes, you can set the input to 0 and calculate the response, right, for 0 input. And you can set initial conditions to 0 and solve to figure out the 0 state response to input. But now, if I ask you what's going to be the total response, you don't know. You don't know how to combine. It's not simply adding them. You need to do some other complicated operation that you cannot figure it out easily mathematically. Okay? So simply, as I mentioned, to get this, you simply solve this equation to get the 0 input response. You go to this one and you forget about the part on the input. You set all inputs to 0, so you end up with only the Q of D applied to Y of T is equal to 0, and you solve this differential equation. And by solving that, you get 0 input response. To get the 0 state response, you solve the whole equation, but you assume that your initial conditions are all equal to 0. And once you get those two solutions, you combine them together by adding them, you get the overall response or the total response of this system for any particular input and any initial condition. Okay? طيب. Now let's focus a little bit on calculating the 0 input response, and this is the last thing that we will discuss today, inshallah. So 0 input response, we call it Y0 of t, to differentiate that from the total response, which is Y of t. As we mentioned, to calculate that, you simply set the input to 0, so you are trying to solve this differential equation. Don't forget that this is actually, this Q of D is just the derivative to the power n, or sorry, the nth order derivative plus some constant multiplied by the n minus 1 derivative and so on until you get to the first derivative, and then you get to the y of t directly multiplied by a constant. That's going to be your differential equation that you need to solve, right? Now, in order for a differential equation to satisfy this condition, and mathematically you can go and check your math course why this is the case, this is only satisfied if and only if this y of t is of a shape that maintains its function shape even after taking its derivative. What is the function, or what is the expression that maintains itself when you take its derivative? It's e to the power time, right? E to the power x, or the cosine and sine, but after every two derivatives. And we know that the cosine and sine are eventually e to the power x, right? We discussed the complex exponentials and how they map to sinusoidal functions and so on, right? So the general case is, it must be that y of t is of the form of e to the power something multiplied by t, right? And of course we have always some constant here that depends on the initial condition. So eventually all what we need to do is to figure out the value of lambda. We will find from here, from this equation, again, if you just substitute e to the power lambda in this equation, you will get this one, right? So instead of y of t, you substitute c e to the lambda t here, and then the result of applying this differential equation is going to be this. For this to be equal to 0, there are two ways. Either t goes to minus infinity, which is not really what we are looking for. That's a trivial solution, which means that everything decays at infinity. Forget about that. Or this equation is equal to 0, right? That's the non-trivial solution. This equation equal to 0, we have here an nth order equation in the variable lambda, which means how many possible solutions for this? N possible solutions, right? So lambda in general can have n different values that can give you a 0 as a result, right? If you solve the second order equation, there are two solutions for x. Third order equation, there are three possible solutions and so on, right? We call those solutions lambda 1, lambda 2, up to lambda n. And for each one of them, there might be a different constant, just to generalize the solution. In general, if for a differential equation, there are two solutions, the sum of those two solutions is also a solution to the differential equation. So that's why we say that if we have n possible solutions, the general solution for y of t is the sum of those different possible solutions with different constants. Okay? خلاص؟ ده math. I don't really care. What I care about is to figure out that this is the general solution that we get to. So we are not required to do this derivation. It's just for your understanding. تمام؟ The target is to solve this mathematically, and as you studied in your math course, this is the general solution. Now this general solution can have some special cases, right? The special cases are addressed in the next slide, again to remind you of them. The first, the representation that we saw in the previous slide assumes that the lambda 1, lambda 2, and lambda n are different from each other. So there are n distinct solutions, right? Sometimes you might have one or more of those roots repeated. So rather than having q of d, which is of q of lambda, sorry, which is of order of n as separate ones, it might be that this and this and this, the lambda 1, lambda 2, and lambda 3, for example, are exactly the same. So it's lambda minus 1, and lambda minus 1, and lambda minus 1. So lambda minus 1 raised to the power 3. We call that repeated root. So the root here, which is 1, lambda minus 1 equals 0, معناها lambda equals 1. تمام? So that root is repeated 3 times because it's of power 3. And then you have the remaining n minus 3 roots. تمام? Distinct. In that case, the solution changes a little bit, and you have the t and the t squared and t up to t to the power r minus 1 multiplied by the exponential. تمام? This gives you the effect that you have the same lambda 1 appearing here multiple times raised to the power r. Yes?
متى بيكون repeated roots متى distinct roots؟
ده depends على الانترنال system نفسه. يعني فور اكزامبل لو انت عندك similar RC circuits connected واحده ورا الثانيه نفس الار ونفس السي then you will have the same واحد على RC هي فالروت بتاعك هو ف you will have this solution repeated 3 times. Then you have another value of a capacitor or resistor in the next RC, it will give you a different root and so on. So it depends on how the system is built. Okay. يا شباب. So that's a special case. The other special case is the roots. When you try to solve these roots, lambda 1 or lambda 2 or lambda, some of them are complex. So they are not real values. In general, when we are dealing with real physical systems, the overall system is a real system. You put a real signal to it and it produces a real signal. It cannot really work in the imaginary space, right? If that's the case, then those roots that are complex, they will appear always in conjugates. You will have a root lambda and its conjugate. So for example, if this is 1 minus I and the other one is going to be 1 plus I. Or if this is 1 minus 3I, this is going to be 1 plus 3I, right? So they will always appear in complex conjugates, and when you combine them, eventually you will get in the solution a sinusoidal representation. Because e to the power lambda, right? E to the power lambda I and t multiplied by added to it e to the power minus lambda I t. When you combine those complex exponentials together, they give you a sinusoidal function, right? The other thing to notice is we said that we have several constants here in this. How do you determine these constants? They are determined always by the initial conditions, right? So you need the initial conditions in order to fully solve the system. It's not just the differential equation, but also you need the initial condition. Don't forget that here we are trying to calculate the response only due to initial conditions. No input. We set the input to 0. Remember? Last thing, just naming. Those lambda i's, the different lambdas that appear in this solution, we call them the characteristic roots of the systems. Sometimes they call them the eigenvalues of the system. Sometimes they call them the natural frequencies of the system, especially that when they appear in the cosine and sine functions, right? Okay, these are all different names to those characteristics of the system. And the exponentials corresponding to them are called the characteristic modes or the natural modes or simply the modes of the system. Okay? So we have the characteristic values of the system are those lambdas, and then e to those lambdas is what we call the characteristic mode of the system or the mode of the system. Right? Again, the reason for the naming is going to come from a quick description that we will have the next slide, okay? Before solving for these examples. Why we care really about the zero input response? Because this is how we understand the general natural behavior of our system whenever something suddenly happens to it. So I have a capacitor which is charged, for example, and connected to an inductor and a resistor. Okay? But this circuit is open. Okay? Now, at some point, I close the circuit. So this system starts behaving without any input put to it, right? I close the system, I finish the connection of the system, right? Now, how does this system behave is dependent only on initial conditions because the capacitor was charged, right? It's going to behave differently if the capacitor was not charged, right? And the other thing is what are the components inside that system. So only rely on the state of the system, and the state here is the components and the initial condition, I can figure out how does this system behave. And that's important for, as I mentioned, sudden behaviors. One example of sudden behaviors, you are driving a car and you are hitting a pump. Right? So you drive a car and then the suspension system hits a pump. Let's say that it was a quick hit, right? What's going to happen to that car? Depending on the initial condition, which means that whether that car was like abnormal or it was pressed because it was loaded by some people or heavily loaded, right? And then this is the initial condition, and then all of a sudden, it just gets into a sudden effect. the behavior of that car is going to rely mainly on its initial condition and design of the suspension system. So if I know that the suspension system, natural behavior, the case when you analyze the suspension system without any input, generally has a behavior which is exponentially decaying, then this means that the suspension system is going to hit this, and then the car is going to move a little bit up and down on the suspension and then continue. If I notice that in the initial analysis with zero input that has some sinusoidal, then after hitting the pump, the car is going to go to do this, but with decaying sinusoid, right? So when you have a car with very weak damping or the مساعدين يعني, تمام, the trusses of the car are called the trusses.
Shock absorber.
The shock absorbers, تمام, they are not in good condition. You see that if it goes through a pump, it stays like for a while, it stays oscillating for a while, right? While another car which is in good shape, it just goes through the pump and it absorbs a good amount of the shock, and then it settles very quickly through a damping exponential only without any oscillation to its final stable condition. So understanding the behavior of the system without input is very important to know what's going to happen when I put input. In general, again, for a particular system, those modes or those different roots or those different characteristic values are representing what we call the resonance response of the system, which means that for those particular values or for those particular time constants, or we call them frequencies, when they get represented into cosine or sine functions, right? The system can sustain the input going through it or sustain the value going through it without any additional push from the input side, which means that if you excite the system on that particular frequency, it can keep on going and it might actually break down. So you always try, when you are designing something, to avoid exciting it at its resonant frequency, except if you really need that, which is what we do, for example, when we are designing oscillators. You just put some trigger to the oscillator and it keeps oscillating forever, right? You only need a DC to maintain it oscillating. You don't need any other varying source for that, right? In that case, we are particularly exciting the system at its characteristic frequency, and then we leave it and it maintains that forever. Okay? So sometimes you want this, sometimes it's not desired if you're looking for stability issues particularly. Okay? That's why we need to study the response of a system to a zero input, right? I think we reached the end of the lecture. I was planning to solve these three examples with you today, but maybe we can do them next time. That's the last slide for today. I was planning to do this example, but we can do it next time. Shukran.